Alright, so in this video I'm gonna be explaining another important article with the title Edge Contraction Pooling for Graph Neural Networks. This paper in 2019, and even in the previous video there was an article, ICLR article that was rejected. They drew inspiration from this paper. So graph neural network research has concentrated on improving convolutional layers with little attention paid to developing graph pooling layers. Yet pooling layers can enable GNNs to reason over abstracted groups of nodes instead of single nodes. To close this gap, we propose a graph pooling layer relying on the notion of edge contraction. Edge pool learns a localized and sparse hard pooling transform. We show that edge pool outperforms alternative pooling methods. Remember, now we are in 2019. In this paper is about 2019. So state of the art is low at this time. So you see the edge pooling is just based on contraction of two nodes, very similar. And because the contraction still keep it connected, it makes the graph connected. That's why it has very good topological properties. So edge pool can be integrated in existing graph classification architecture. It can also be used for node classification. So I've explained diffpool in a different paper. We know that it has computational complexity problem, although it's very good because you fix the number of clusters. On the other hand, it's not good to fix the number of clusters because you are disrespecting the distributions of the graphs. So top K pool is also another good paper. You get top, but you know these problems of top K pool, sag pool, they always try to somehow ignore the graph topology. So edge contraction, when we have an edge that we compute the raw score. So assume that we have an node I and then node J. So R is the raw score that we associate to this edge, REIJ, because this is an edge connecting node I to J. So we concatenate, giving to linear with bias, and then you get the score. But this score, you need to normalize it, the softmax of that, to get a better final score. Then you go through this. As you see, there is just merging of nodes. There is nothing new. But to enable gradient to flow into scores, we use gating, multiplying the combined node features by the edge score. And then integrate, also you can do integrating edge features, which is amazing. Very simple idea, very simple paper, but very profound. And most bio-inspired, things that you see in our body, in our brain, is just they are simple processes, just simple message passing. So simplicity is the core of intelligence. And then we have graph classification. You can apply it for node classification. But remember, these Cora, Sightseer, PubMed that I always see, they are just for they are highly homophilous, not heterophilous. It means that for any node, the neighbor nodes are very similar to each other. Maybe only one outlier, but the rest of them are very similar, have similar labels. And so that's not fair to do node classification only on these types of data sets. We need to go beyond. And state of the art for heterophilous graphs is just around 50%, 40%. It's amazing because we are in 2025. Our accuracy in the world is very low, and they think they have become God. So you see that how human brain is too far from AI, this naive AI that we are working on. I mean, there is a huge gap that even for a heterophilous graph, state-of-the-art in the world, I mean, 10 billion people in the world are working on that. State-of-the-art is just 50%. This means that we are not interested in science. So does edge pool outperform alternative pooling approaches? This is a very research question, good research question that they have done it experimentally. Another one, can edge pool be integrated in existing architectures? And then this protein is a very popular benchmark for graph classification. Even in 2019, with this algorithm, we could have 72% accuracy. Of course, with a little bit high variance, but it's good. That's a simple algorithm and simple hierarchical pooling algorithm, state-of-the-art 72. That's good. And then, can edge pool be used for node classification? And then, for proteins, for collab, for example, graph isomorphism network is really important. Graph isomorphism, I always remember like this. It's an MLP of the edge in itself plus, of course, epsilon edge plus some aggregation, traditional aggregation, summation of neighborhood messages. And so we update in the next layer K based on layer K minus 1. Aggregation is over nodes in layer K minus 1. And also graph convolution. You see graph isomorphism network is better than here, is better. But for node pooling and edge pooling is, let's say they are the same if you compare GCN with GI. But let's see for other types of, for even MLP is comparable. For Cora, you can compare again in graph isomorphism network. This one is a little bit lower than this. Lower. So you see, for node classification, we can say lower than this. With the node classification, we can say that graph isomorphism network is not performing well. Let's do a reflection and see why. MLP of H plus epsilon H plus the aggregation. So what are we missing that in node classification we have this? Because you are aggregating, and this sometimes deteriorates the performance. You know that for node classification, sometimes MLP, just using MLP is enough to get a high performance. But they have when you have a heterophilous graph, your aggregation deteriorates the performance because you have many different colors, many different node neighbors in the neighborhood. So your aggregation should be very, very careful. That's why we care about feature-wise, to see which features are GNN, let's say, favorite, which features are GNN disfavorite. And then they use it for node classification.